Hello, everyone. Can you hear me?
Yeah.
Yep. Okay. Yeah, so this is our 14th discussion. We're going to do graphs in quiz 5 and maybe a review problem. Yeah, so I'll have office hours tomorrow. I don't know about Ilkin, and there's two review sessions on Monday during Zoe and James's office hours. And your final is on Thursday from 3 to 5. So any questions before we start? Okay. So for this problem, we have prove that for a simple graph G, in which all of the n nodes have a degree of at least 2, then there are at least n edges. So we'll begin by writing the definition of a simple graph. So it's simple if there are no loops. So you can't have this situation. And there are no parallel edges. So you don't have something that's like this. So to start off, we have n nodes, and each has degree 2. So we know that for all, let me rewrite this, for all vertices, the degree of each vertex is greater than or equal to 2. And so if we take the sum of the vertices, the degrees of the vertices, then this is greater than or equal to 2n. Everyone good with that? And that's because we have n vertices and each has degree at least 2. So yeah, so we can look at theorem 3, which says that for any graph, the sum of the degrees of each vertex is equal to 2 times the number of edges. Okay, so we have a question. It says, is it possible for each vertex to have at least 2 degrees to not have a loop? Is it possible for each vertex? Degree 2 and not have a loop. Oh, okay, yeah. So right? So the degree is the number of connections to other vertices. So, something like this, or not directed. Something like this has degree 5 for this vertex. Does that answer your question? Yeah, a loop is different from a cycle.
Isn't a loop
what?
Isn't a loop just where it's the same two vertices, one there and one back? Where a cycle has it between any. So
yeah,
any of those 5 can be connected to each other. They just can't connect back to the center.
Yeah, so this is a loop here. So to answer the question, so you'd have a cycle there. But we're not worried about cycles. Okay, is everyone good on that? Okay. Okay, so where were we? 3, which says any graph, the sum of the degrees of each vertex is equal to 2 times the number of edges. So if we look up here, this is why we're looking at theorem 3. We're trying to show that there's at least n edges. So the number of edges, so capital E is the set of edges. So the size of that is equal to the sum over the vertices of the degrees. And from our assumptions, we showed that this is greater than or equal to 2n. And this is 2 times. So 2 times the number of edges is equal to the sum of the degrees of the vertices, which is greater than or equal to 2n. So rearranging that, we can say that the number of edges is equal to the sum over the vertices, the sum over the degrees of the vertices divided by 2, and that's greater than or equal to n. And that shows the claim. Any questions on that?
Where did you get the 2n?
Where did I get the 2n? Okay, so this 2n?
Yeah.
Okay, so we have n edges, right? So I'm going to switch to another one. So we have n nodes or n vertices. Nodes and vertices are the same. And for all v, all vertices v, the degree of v is greater than or equal to 2, right? So if we take the sum over v in v, then of the degrees of each vertex, this is equal to, the sum from I equals 1 to n of the degrees of the vertices I, right? Each vertex vi, if we labeled them. And this is less than or equal to, no, sorry. So the degree of each vertex is greater than or equal to 2. So I can rewrite this as this sum here is greater than or equal to the sum from I equals 1 to n of 2. And since we're adding 2n times, this is equal to 2n. Is that good?
That was still a bit confusing.
Okay, where did you go?
Yeah, I guess the notation is what's confusing me. I think I'd understand better if they were formatted into words.
Okay. So each vertex is at least degree 2. Yeah, so there. The sum over n vertices, where the degree is greater than or equal to 2, is at least 2 times n.
Oh, okay. Yeah, that makes
Yeah.
sense.
Okay, good. Any other questions?
Yeah, would this carry to be true if like the least degree was 3, then the sum of the vertices would be at least 3 times n?
Yeah, so if let's write that. So you're saying if the sum over v and v, degree of v, and you're saying if the degree of v is at least 3.
Yeah, 3 or 5 or 7 or whatever.
Okay, so let's just do it with 3. 3 times n. We would get from theorem 3 that the number of edges, 2 times the number of edges would be greater than or equal to 3n, right? So that would mean that the number of edges is greater than or equal to 3 halves n. Right?
Oh, okay, cool.
Yep. And then, for m edges, you would get n, the number of edges is equal to m over 2n. Yep. That good?
So in that formula, though, if you have at least two, wouldn't you get just number of edges equals n? Or is it greater than or equal to it?
Where? Which
So what you just wrote down was the number of edges equals m over 2n.
Yeah.
Is that greater than or equal to? Not equal to?
Yes, it's greater than or equal.
Because if m, I was like, if m equals 2, like we just showed.
Yeah,
we
it's greater
talked
than or
about
equal.
it being 2n.
Yeah, it's greater than or equal. Yeah, so the only special thing about 2 is that theorem 3 talks about 2 times the number of edges. So 2 divides 2. Yep. Anything else? Okay, this one's an easy one. So the first thing is we're going to draw the graph and then do the adjacency matrix for the relation. So we have our nodes in A, which are labeled 1, 2, 3, and 4. And our relation is these pairs where 1 goes to 1, 2 goes to 3, 3 goes to 2, 4 goes to 1, and 4 goes to 4. So I'll give you a minute to draw the graph. Okay. So when you're doing this, just remember, make sure you have all your vertices in the graph and go through these one at a time. So we have a edge from 1 to 1, so that's a loop. An edge from 2 to 3. An edge from 3 to 2. An edge from 4 to 1. And a loop on 4. Hopefully you got the same result. And then we need to do the adjacency matrix. So does anyone know what that is?
I think I do.
Yeah, go ahead.
Okay, I have 1, 0, 0, 0.
Okay, yeah, so
Am I doing it wrong? Wait,
no, you're doing it right, but
do you want
yeah,
to
so
explain
what-
what it is first, or
yeah, what the adjacency matrix
Okay,
is.
so I have the vertices like in rows and columns. So you have
Okay.
a ones row, a twos row, a threes row, and a fours row.
Yep.
And then a ones column, a twos columns, a threes
Yeah.
column, and a fours column.
Yeah, exactly.
And then at 1, 1, if there's a connection from 1 to 1, I put a 1.
Yep.
So, and if there's not a connection, you put a 0.
Yep. Exactly. So yeah, there's one other point is that we have a connection. We have a convention, right? Because there's two ways you could write this. So we say that the rows are from and the columns are to. So, you know, the question is whether a circle is a terrible thing to put there. Whether 4, 1 is here or if it's down here, right? So our convention is that this is from in the rows and 2 in the columns. So 1 doesn't go to anything, so the rest of these are 0. For 2, 3, we go from 2 to 3, so we put a 1 there. For 3, 2, we go from 3 to 2, put a 1 there. 4, 1 is right here from 4 to 1, and 4, 4 is there, and then the rest of this, as Jackson said, is just zeros. Everyone good on that? There might be something like this on the final, probably.
If there is more than one edge between a place, do you put a 2? Like,
Yeah, so no, but remember, so these are sets, right?
yeah.
Yeah. I'd have to think about that, but
Because you can have like parallel edges. Does this only work for simple
Right.
graphs?
I don't know. This is a simple graph. I'll look into that.
This isn't a simple graph, but
Why? Oh yeah, it's not a simple graph because
there's
loops.
loops.
Yeah, Wikipedia says it's a 0-1 matrix, so
Okay.
I think it's just whether there's a connection.
Because there's a different kind of matrix than where you put numbers.
Yeah, there's other kinds, but this is just adjacency matrix. Yep. Do all sorts of fun things. Do these only work for directional graphs? Well, kind of, right? So we can make this non-directional if we put a loop here, if we put an edge from 1 to 4, right? So that would make this 1 up here. And if you have a non-directional graph, a non-directed graph, then it's going to be, the matrix will be symmetric about this diagonal, right? Because, if it's not directed, you could just view this as two edges in a directed graph. Good question. And I'm going to undo this so that the scribble appears like the actual solution. Okay. Any other questions?
I have a question.
Yeah.
On a problem that's similar to this. If we had a set A where we didn't use all of them inside of the relation, would they pop up in either the graph or the adjacency?
Yeah. So you're talking about, like, let's say that there's 5. Let's just go back here. Let's say that there's a 5, right? Is that what you're saying?
So yeah, there's a 5 inside of A, but it never appears inside.
Yeah. Okay. So in that case, you would have, for the row here, you would have zeros here, and you would get a column of zeros over here. So yeah, you could draw it there. Well, you would need to.
And just a comment, you forgot to erase one of the edges from the picture that you drew.
Thank you. We'll use the eraser. Okay. That it? Okay. Nope. Okay, so this one is saying that we have two vertices u and v in a graph G, such that there is a walk from u to v in G. Then there exists a path from u to v in G. So let's start by writing down our definitions. So so a walk, what is a walk? Someone want to volunteer?
List of vertices and edges.
Yeah, okay. It's a list of alternating vertices and edges. Okay. And then a path. What is a path?
Is that a walk with no repeating edges?
Yep. Let me make sure. Pretty sure it's not repeating vertices.
Oh.
Yeah. Close. No repeated vertices. Okay, so what we're trying to say is we have a walk from u to v. So we can write our walk down. So we go, so if we say v0 equals u and vn equals v, then we go e1. So we go from v0 via e1 to v1, e2 to v2, and so on. And then we get to vn minus 1 to en to vn. All right, so the way we're going to approach this, so we know that there is a walk from u to v in G. So this walk exists, and I'm going to call it W. And we're trying to show that there's a path. So what we're trying to say is that there's a walk that doesn't have duplicate vertices in it. And one way we can show this is we can say W is the shortest walk among all walks. And this will exist because we know that there is a walk from U to V. Is everyone good with that? Yep. Okay, so we're going to do proof by contradiction. And so our assumptions are going to be that W is the shortest walk from U to V in G. And so remember our conclusion, there exists a path from U to V in G. So I'm going to say, and W is not a path. Because if W is a path, then that would be a contradiction to not existing a path from U to V and G. So we wrote down that W equals V0, where V0 is equal to U, E1, V2, so on, Vn minus 1, En, and Vn, which is equal to V. So if it's not a path, then there is an I and a J with one second, let me rewrite this. There exist I and J such that I is less than J, where Vi equals Vj. So what we're saying is we could come in here and find E, that's a 1, EI, VI, EI plus 1, and then we would have V or EJ, VJ, VJ, EJ plus 1. We could cut this part here out of the path W. So we remove the section, the sequence, subsequence between EI plus 1 and VJ. So if we look at this, we get W prime is the shortened sequence. And we notice that the length of W prime is less than the length of W, but we assume that W is already the shortest walk, and W is still a walk, so that's a contradiction. W prime is shorter than W, and W prime is a walk, contradicting W being shortest. So that's the contradiction. And that means that, that there is a path in this graph from U to V. Any questions on that?
So if I is less than j, how can vi equal vj?
Okay, yeah. So this is in the sequence, right? So I and j are just indices of W. I should put commas here, shouldn't I? Does that help? So I'm saying that the vertex, so in this list, so let's say that our vertex is A, right? I have some edges in between. And then A pops up again over here. This is going to be Vj, and this is Vi.
Oh,
Maybe I should say Wi. Does that help?
I think that makes more sense. Yes.
Yeah,
I thought we were just
yeah.
naming
Sorry.
the vertices, not indexes.
Yeah, okay, yeah. Sorry, so this is W, right? And then we go and look inside the sequence to find where this happened, and then we can delete this section here and just go from this edge to the end. Any questions on that?
I have a question.
Yep.
Can you go over how you got W prime again?
Okay, yeah. So I looked inside of W and I said, okay, W is not a path, right?
Yeah.
So it's not a path because there's some place inside of here where the same vertex shows up, right?
Yeah.
And I said, okay, well, I know that EJ plus 1 leads out of VJ and it will go to V at the end. So I can delete this whole thing in between. And that's how I got W prime, is this deleted C. I deleted this portion of W. And it's still a walk. Actually, here, let me have, I think a drawing might help. So this is U and V. And then we have this. So let's say we have a walk that goes like this. If I delete this portion, it's still a walk, right?
Yes.
Yeah. So I said that I had the shortest walk. If this is not the shortest walk, because I can delete this part, right?
Oh, yeah.
So that's this. So W would be, W would be this walk, and W prime would just be that walk. Does that help?
Oh, okay. I think I get it now. Thank you.
So did you just decide that you had the shortest walk? Like, is that just
Yeah,
like
well,
an
there's
assumption?
there's always going to be a shortest one, right? You know that there is a walk, right? And you can write down every walk in the graph, right? And you can choose the shortest. All you need to say is that there is a walk to say that there is a shortest one. Yep.
Is that a pretty common like proof technique? Just assuming that you have the shortest walk?
Yeah, actually, or you have the minimal example. So these come up in like the algorithms class all the time. So you say, I have the shortest, the smallest example, the minimal example, that type of thing. Yep. Any other questions? If there is a walk, is there proof that it is a shortest walk? you can't prove that any walk is the shortest walk. You can just say that I know there is a walk and I can find a shortest one. Oh, okay. No, you know that that one exists. Yeah, okay. So, so let's say we have, we know there is a walk. So there's walk 1, walk 2, walk 3, walk 4, right? You can compute the lengths of each of these, and you get the shortest one. So you have, okay, let me, so you have all these, you know that a walk exists, right? Which means that you can write down a walk from U to V, which means that it's possible for other walks to exist. And you can always choose one that is the shortest. Does that answer your question? Yeah, so the question is, if there is a walk, is there a proof that there is a shortest walk? And it sort of seems like I'm just waving my hands, but you can just say that, you know, if something exists, you know, so if there exists E, then you can find, you know, you can measure, you can find the length of each walk and say that you have the shortest. And actually this, if you want, you can use this as a proof. So as a proof of sorts that you can always shorten a walk if it has these cycles in it. Okay. Oh, any other questions? Okay. So we're going to have a graph G that is a bipartite graph, and we're going to prove that every cycle in G has even length. So does anyone remember what a bipartite graph is?
Isn't it a graph that you can split into two pieces?
Yeah. Okay. So there's two partitions. Of V, and we call those V1 and V2. Right. So remember, a graph is a pair of vertices and edges. And we have V1 and V2 as the partitions, where V1 intersect V2 is empty, and V1 union V2 is equal to V. And so it's a bipartite graph. This partition is induced by the relation from the edges. So we know that we only have edges from V1 to V2 or from V2 to V1. And so just so we can get a little bit of a sense of how this is going to go, let's say this is V1, this is V2, and we have a few vertices over here, a few vertices over here. So we have a cycle that goes from V1 to V2. So one example cycle is this. And we can see that we have 1, 2, 3, 4 edges in our cycle, and that is even. And we're going to show that this occurs for every graph, every bipartite graph. And every cycle looks like this. So sorry. So let our cycle be, our cycle C is going to be the list of vertices. Nope. First, let's choose a vertex. I'm going to choose vertex 0. So that's our start point. Okay, we'll have a cycle starting from V0, and V0 is in V2. I'm just doing this for convenience. And we can write down our cycle as a list of vertices. So we know we have V0, V1, V2, V3, so on. Then we get Vn minus 1 and V0. And so we can use the definition of a bipartite graph. And we know that since V0 is in V2, that means that V1 is in big V1. And then, right, because, yeah, V2 is in V2. And that's because big V1 can only has edges going to V2. And V2 only has edges going to V1. So to get from V2 to V3, we know we're following an edge from big V2 into V1. And we can do this repeatedly. And we can look right here and say, okay, so we're now in the situation, oops. So we have V0. Something is coming in from V0 from Vn minus 1. And that means that, by the definition of bipartite graph, Vn minus 1 is in V1. So if we look at this, every vertex in this list that is in V1 is odd, right? And that means that n minus 1 is odd, which implies that n is even. Oops. Here. So, Vn equal to V0 is even. And so if you look at the length of this cycle, right? So the length of the cycle is equal to n plus 1, but we're actually counting the edges, so we subtract 1 to find cycle length. Yes. So, right, so because we're looking at the cycles, or we're looking at the edges that form the cycle. So you subtract 1 because that's duplicated. So the length of the cycle is n, and n is even. Any questions on that?
Could you do a proof by contradiction here? I feel like that would be easier. Maybe. I don't know.
Okay, yeah, you could. So that would go like, so we say that we have a cycle in this bipartite graph, and it has odd length, right?
Yeah.
So then you would get this, you would go through this work right here, and you would show that the cycle actually is even length, right?
I guess I feel like you'd show that, wouldn't you prove it wasn't a bipartite graph? Or like show it would have to not be a bipartite
Okay,
graph?
yeah, you could also do that. You could also say, okay, so in order for this to be odd length, okay, yeah, so you assume that it's odd length. For this to be odd length, you had to have an edge in here, right?
Mhm.
And then you would say, okay, but it's not a bipartite graph anymore.
Yeah.
Yeah,
Would
you
that
could
be
do that.
Would that's a contradiction, right?
Yeah, that's a contradiction because you assume
Yeah.
it's a bipartite graph
Yes.
and cycle length is odd. And you'd say, yeah, it either appeared over here or over here, this imbalance.
Hmm. Okay.
I'm going to cross these out for someone looking at the scribble. Any other questions?
I have a question.
Yeah.
What is n exactly, and how did you get n?
Oh, okay. Sorry. I was a little sloppy in how I wrote this. So n is the length of the cycle. And it's equal to the length of the list C minus 1, right? Because you have an edge in between each of these. So, if you have 5 things, the things in between is n minus 1. Does that make sense?
Whoa, wait, can you say that again?
Okay, so I wrote down the list of all vertices, right, in the cycle.
Mm-hmm.
And the length of the cycle is the number of edges in the cycle, right?
Length of cycle equals length of edges.
Yeah.
Or number of edges.
Yeah. So I have n plus 1 or n things here, or n plus 1 things, right? Because I have this duplicate element, this v0, and there's going to be n things in between them, which are the edges. So there's n edges in there.
N edges, okay. And how did you know n minus 1 is odd?
N minus 1 is odd because this vertex right here, this vertex here is in V1. And we were noting that it goes even, odd, and then we end with an even. So this one must have been odd.
We end with an even?
Yeah, because the only way to get from to V0 is from partition 1, V1 right here, right? And we know that the sequence goes even, odd, and then we're ending with an even, so this one must be odd, which means n minus 1 is odd.
V0 is even?
Yeah, because it starts in V2, right? The index is 0 up to n.
Oh, 0 is even?
Yeah, 0 is even.
Oh, okay. 0 is...
Yes, it's 2 times 0. It's the easiest one. Any other questions?
Thank you.
Okay, so I guess maybe we'll quickly go over 2 of your quiz problems. So how many different ways are there to form 7-digit strings having no zeros? Okay, so no zeros means our digits are in 1, 2, 3, 4, 5, 6, 7, 8, or 9. So we don't have 0. Where we only distinguish between the number of appearances of each digit, meaning the sequence with 4 7s and 3 5s, and 3 5s and 4 7s are the same number. But if we have 3 5s and 2 5s and a 4, these aren't the same under our rule. Everyone good with that? So the way we can look at this is we're trying to find how many ways we can write down numbers, but we don't care about order, and we can have repetition. So this means that it's a binary sequence problem. And we can have n plus 1, n1, n2. So n1 is the number of digits that are 1, and 2 is the number of digits that are 2, up to n9 equals 7, so the number of 9s. And the total length is 7, so we know it's a binary sequence. We know we have 9 things that we're putting into 7 places, or we have 7 things, 7 slots. So our formula is going to be choose 7 plus 9 minus 1. And we choose from that 9 minus 1, and that's equal to choose 15, 8. Does that make sense? Yep. How was the quiz? By the way.
Well, I found it a little painful.
A little painful, okay.
It was hard for me.
It was hard? Which problems were hard?
Oh man, I can't really remember.
You can't remember, okay, that's fine. I know, I don't know where grading is. It's supposed to be done on Friday though, so, or tomorrow. I guess tomorrow's Friday. Yeah. Okay, so let's answer the previous problem with the constraint that each instance can have no more than 2 7s. So you can do this with the rule of complement, and so we need to count the number of numbers with 3 or more 7s, and we can do that, so we can do that by saying set n7 from earlier is greater than or equal to 3, and we can come up with n7 prime, which is equal to 0, but we have to take off 3 slots from the sequence. So we get our total, which was 15, choose 8, minus, by the rule of complements. So we do choose 7 minus 3, because we already gave 3 to the 7, plus 9 minus 1. And then we're still choosing from the other 9, so we get 9 minus 1. That's equal to choose 15, 8, minus choose 4, 13, 12, 8. You could have also done that one by cases. And then this other one, I'm going to go really fast. This one is we have 15 fourth graders, 15 fifth graders are standing in a line. Assume that every way they can line up is equally possible. So we are asking for the chance that they appear in alphabetical order by name, and that's 1 over 30 factorial. If you want to look that up, it's similar to the problem, the birthday party, or not your birthday problem, where you have the probability of 2 people having the same birthday. The second one is we have an alternating where we go fourth, fifth, where the fifth graders, all 15 fifth graders are first, and then we have the fourth graders. And so there's 15 factorial ways to get the fifth graders here, and then 15 factorial ways to get the fourth graders, and that's over 30 factorial. You can watch other things for this. And then the last one is tricky because you can either start with a fourth or fifth grader. So it's 2 times 15 factorial over 30 factorial. You can watch other discussion sections for more detail on that, because we're really out of time. So thanks everyone for coming. Come to office hours and the review if you have more questions. Yep, it's been a good semester. Thanks.